Greetings and salutations. Today, we will be talking about matrix determinants. How do we visualize a determinant? And what is it really telling us? What does the magnitude of the determinant tell us? And what does the sign of the determinant tell us? As always, let's start by visualizing a transformation. I've drawn a 1 by 1 square, and we're going to apply the transformation defined by the matrix 3, 1, 1, 2. As we do, the square turns into a larger parallelogram. But how much larger? How much did the area change during the transformation? Let's look at a bunch of figures and see how their areas change. When we apply the transformation, we can see that each of these figures has gotten 5 times as large an area. It is no coincidence that the determinant of this matrix is 5. The magnitude of the determinant measures how much the transformation changes the size of the objects. Now, what we mean by size depends on how many dimensions we're in. If we're in R2 and transforming a two-dimensional shape, then the determinant is an area scaling factor. The area of a two-dimensional shape gets multiplied by the determinant as the transformation is applied. When transforming three-dimensional shapes with a 3 by 3 matrix, the determinant is a volume scaling factor. If we look at the grid, we can see what's really going on. I've highlighted a single grid box here, which has an area of 1. What the magnitude of the determinant tells us is the area of a single grid box in the transformed grid. In this example, a single grid box has an area of 5, and so the magnitude of the determinant is equal to 5. Let's look at another transformation. In this expansion transformation, the area of a grid box is equal to 3, and so the magnitude of the determinant will be equal to 3. In this rotation transformation, the area of a grid box doesn't change, and so the magnitude of the determinant will be equal to 1. This next example will be a non-invertible transformation. We can tell because this transformation is not 1-to-1 or onto. There was squishing during the transformation. This caused the area of the grid box to become 0, which means that the determinant of the matrix will be 0. Any non-invertible transformation will squish the grid into a lower dimension, and this is why the matrix of a non-invertible transformation will always have a determinant equal to 0. So now we've seen that the magnitude of the determinant is the size scaling factor. But what does the sign of the determinant tell us? Let's again look at an example transformation. But this time, we want to pay attention to the angles in the transformation. For now, let's look at the angle between the basis vectors 1, 0 and 0, 1. Notice that the angle is counterclockwise, which is what we consider the positive orientation. However, when we apply the transformation, the direction of the angle changes. Now the angle is oriented clockwise, which is the negative orientation. The determinant of this transformation is -5. The negative determinant is what caused the angle to change orientation. Orientation in R2 can also be visualized as a circle around the origin. A positive orientation will mean that a particle will move around the circle in a counterclockwise motion. But when we apply this transformation with a negative determinant, the particle now moves around the origin in a clockwise motion. A negative determinant reverses the orientation of angles from positive orientation to negative orientation or vice versa. Let's now look at a matrix transformation with a positive determinant. We will again start by looking at the angle between the basis vectors. This time, when we apply the transformation, this angle remains counterclockwise. This is because the determinant is positive. As we did before, we can also look at the counterclockwise motion around a circle and see that when we apply the transformation, the motion remains counterclockwise. When the determinant of a matrix is positive, the transformation preserves the orientation of angles. So what should we take away from this video? The magnitude of the determinant of a matrix is the scaling factor by which the size of objects change during the transformation defined by that matrix. If the matrix is 2 by 2, then we're talking about the area scaling factor. If the matrix is 3 by 3, then we're talking about a volume scaling factor. And in all cases, if the determinant is equal to 0, then the matrix and the transformation are not invertible. This idea also applies to larger square matrices. However, higher dimensional versions of volume, hypervolumes, are not easy to visualize. We also saw that the sign of the determinant shows if the orientation changes or remains the same. For a 2 by 2 matrix, a negative determinant means that all angles or motion that was counterclockwise changes to clockwise, and vice versa. We can also talk about orientation in 3 dimensions using the right-hand rule, but orientation in higher dimensions is harder to visualize. However, in all cases, the idea is the same. If we have a negative determinant, then clockwise becomes counterclockwise, right-handed becomes left-handed. It's like looking in a mirror. Hopefully now, a determinant is no longer just a number to you. The magnitude of the determinant tells you about size, and the sign of the determinant tells you about orientation. And we can now understand why a zero determinant tells you that a matrix is not invertible. Thank you for watching the video, and in future videos, we will talk about eigenvectors and eigenvalues.